Taking a look at worksheet number 19. That was homework from Friday. We'll give you the answers to that, and then you could tell me which question or questions we need to go over. For question number 1, I got an energy in question number 1 of negative 12.09 electron volts. I got a frequency of 2.9 times 10 to the 15 hertz, and I said that was UV light. What I didn't do, I'm just noticing here, is calculate the wavelength of EMR. We were asked for the wavelength, the energy, the frequency, and the type of EMR. I didn't calculate the wavelength, but you know how you'd find the wavelength given the frequency or given the energy. You could say wavelength is equal to V over frequency. That's the wave equation that you learned in Physics 20. Or you could say that wavelength is equal to E over, what is it? E is equal to HC over lambda. So lambda would be equal to HC over E. HC over the energy. So either one of those will get you the wavelength. If you use that method to get the wavelength, then you've got the correct answer. Okay. Question number 2. I got an answer, question number 2, for the energy of positive 12.09 electron volts. Positive because in this case the energy was absorbed. In question number 1, the energy was emitted. You get a negative value for change in energy when it's emitted. You get a positive value when it's absorbed. So it's going to be positive 12.09 electron volts. We're going to have a frequency here of 2.9 times 10 to the 15 hertz again. And it's once again going to be UV light. What's the only difference between question number 1 and question number 2? It's absorption and emission. Question number 1 is making a transition from the 3rd to the 5th level, so it's absorbing EMR. Question number 2 is making a transition from the 5th to the 3rd level. The 1st to the 3rd level, which means it's absorption of EMR, which means it's going to be a positive value. Finally, question number 3. I get an energy here in question number 3 of 0.96 electron volts. I get a frequency of 2.3 times 10 to the 14 hertz. We're looking for the type of EMR. Tell me what type of EMR that is, 2.3 times 10 to the 14. It's infrared, yeah. It's real close to visible light, right? What do we say the range of visible light was? 4 times 10 to the 14 to 7.5 times 10 to the 14. That's not in the range. It's very, very close, but it's not in that range. So we're going to call that infrared light. And we want to know whether it's absorbed or emitted. Because we're going from the 3rd to the 5th level, it's going to be absorbed. And we know that also because we have a positive value for the energy there. Whenever you have a positive value, it's energy absorbed. Negative value, energy given off. Any questions 1 to 3 on worksheet number 19, now that you have the answers? I'll tell you what, I'll do one of them. Yeah, I'm not going to go over all 3 of them here, but I'll go over one of them there. Any preference? Let's do question number 3. Okay, question number 3 says, calculate the frequency of the EMR involved when an electron and a hydrogen atom makes a transition from the 3rd to the 5th level. What we have to do is look at the electron level diagram at the top of the page. The energy of the 3rd level, we're going to say E3, is equal to negative 1.51 electron volts. The energy of the 5th level, we're going to write down as negative 0.55 electron volts. Now, those are the 2 energy levels that I'm concerned about because it's making the transition from the 3rd to the 5th level. To find the energy of the transition, I need to subtract them. But which one do I subtract from what? E is equal to E3 minus E5 or E5 minus E3? How do you know which one to put first? It's like a delta, right? A change. So it's always going to be final minus initial. If it's going from level 3 to level 5, we're going to say level 5 minus level 3, or negative 0.55 electron volts minus negative 1.51 electron volts. When I do the math on that, it works out to be positive 0.96 electron volts. So that is the energy of the transition. That is the energy that is absorbed to cause an electron to jump from the 3rd level to the 5th level. That would be the energy of the photon that was absorbed to cause that transition to take place. Now, if we want to find the frequency, we can use the equation E is equal to HF and rearrange it to solve for frequency, E over H, Planck's constant. hey, that equation is valid. I just got to make sure that I use the right energy here. I can never use the energy of a particular level when I'm using E is equal to h times f. That's not what it means. That energy in that equation that I just wrote down is the energy of a photon. And a photon is always equal to the change in energy, the energy difference between one level and another level. So we have a difference here of 0.96. That's what I'm going to use. What value of Planck's constant would I use? 6.63 or 4.14? 4.14 times 10 to the minus 15 electron volt seconds. Now, let's say you're one of those people that don't like using electron volts because you're not sure when you can and when you can't use it. Could you use joules here? Could you use the 6.63 value for Planck's constant? Yes, you could. What would you have to do if you use the 6.63 times 10 to the negative 34 joule seconds value for Planck's constant? Yeah, you've got to convert the electron volts to joules. And you guys remember how to do that, right? 1 electron volt over 1.6 times 10 to the minus 19 joules equals 0.96 electron volts over x. So I could find the number of joules there and then use the 6.63, but if you spot the fact that you can use the 4.14, it might save you a little bit of work if you do it this way. Doesn't really matter to me at all which way you do it. Just do it whichever way is going to give you the best chance of getting the right answer. Right? Is that good? Caleb, you can come in and see me on this stuff if you need to. Okay. All right. I want you to take a look at this diagram that you see up on the board right now, this picture that you see up on the board. I want you to tell me what you know about this picture. And I'm telling you nothing about it other than, look, there's a picture up on the board. Tell me what you know, what you can learn from this picture that you see up on the board. Okay, so the condensation trails from airplanes. Okay, so you know that, how many airplanes do you have? Okay, so we have 2 airplanes. Okay, what else do you know about this? Okay, let's call this number 1, condensation trail number 1. Let's call this one condensation trail number 2. Which one was the most recent, Alex? Okay, so number 1 was the most recent because that's spread out the least. So we know that we have 2 airplanes. We know that one of them has been here fairly recently. The other one is a little bit further back in time. We know that because the condensation trail has spread out a little bit. Okay, good. What else? What else do we know about these airplanes? I'm sorry? From this point to this point? Okay, so you're saying plane 2 is going in that direction. How do you know that, Jordan? Yeah, the condensation tail is kind of spreading out, and that's going to happen as time goes by. So it is going from top to bottom. It looks to me like number 1 is going this way, although I couldn't say that for sure. It looks like it's kind of spreading out a little bit to the upper left there. We know that they're going not quite perpendicular to each other, but almost perpendicular to each other, right? What else do we know? They're going pretty fast, yeah? We know that they don't collide, right? How do we know that they don't collide? Because it'd be a big condensation trail everywhere here if they collided, yeah? We know that this one looks like it has how many engines? 2 engines. This one kind of looks like it has 2 engines, although it's not really definitive, right? It's kind of difficult to see this, but we definitely have 2 engines there. So we've learned a lot just by looking at this picture of this condensation trail that follows these airplanes. When I started this, put this page up, I just said, what can you tell me about this? I didn't even tell you it was airplanes. You guys told me that there were 2 airplanes flying virtually perpendicular to each other, flying in this direction, not colliding with each other, 2 engines, traveling in straight lines. You told me a whole lot about these airplanes without actually having ever seen the airplanes and without actually having ever been told there were airplanes there. The point that I'm trying to make here with this diagram is that we can do the same thing with subatomic particles. There's 2 ways that we're going to learn about today to observe, we'll call them subatomic particles, particles that make up protons and neutrons. Protons and neutrons, until today, you kind of thought were probably fundamental particles. They don't get any smaller. Today you're going to learn that they do get smaller. We break them down into smaller particles. How do we learn about those smaller particles? Well, we smash them together. It's the ultimate guy's machine, really. We take a particle accelerator. We accelerate these things to incredibly high speeds, incredibly high energies, and then we smash them into each other and break them. And we see what happens. It's like a piñata. You want to see what's inside it? You don't want to take a little broom to it. Take a baseball bat to it. Just give it. The more energy, the more ability we have to overcome forces. In the piñata, it's the forces that, the tape and the glue and all that stuff that we have to overcome. In the particles, like, say, protons that maybe we're colliding together, we have to overcome a strong nuclear force and a weak nuclear force. We have to overcome nuclear forces. Well, it's difficult to do that. So we have to make these things have a ton of energy in order to overcome those forces. We accelerate them to really, really, really high speeds. You guys have probably heard about the Large Hadron Collider and straddles the border between Switzerland and France. And I forget how big it is. It's something like 30 kilometers in diameter, or something like that, something crazy like that. This giant circle where protons, basically, are accelerated to a speed of something like 99.99999% of the speed of light. That actually makes them, that's so fast, that actually makes the particles quite heavy. Because the faster things go, the heavier they get. When they collide, they have a fighting chance of breaking those particles because they have so much energy. Two cars collide together in a parking lot of Walmart. Maybe you get a scratch. Two cars collide on a highway at 110 kilometers per hour, and the cars can break apart. The more energy they have, the more ability you have to break the forces that keeps them together. We accelerate these to really high speeds, really high energies to overcome the forces within. Now, how do we observe what comes out of this? If we smash a proton against a proton, how do we see what comes out of the proton? These smaller bits of matter, these subatomic particles that make up the protons. Well, there's a couple ways we can do it. We can use a cloud chamber. A cloud chamber consists of this dust-free air. So it's clean air. But this dust-free air is super saturated with either water or alcohol. When these protons break apart, you end up with these tiny little charged particles, these charged particles that make up the protons. These charged particles, we'll call them the subatomic particles, enter this cloud chamber. Then they ionize molecules within this cloud chamber. These ionized molecules cause the vapor, and that's exactly what we have here, right, is a vapor, a gas. We cause it to condense. It produces a cloud, a condensation, a cloud. So how do we learn something about these particles, these subatomic particles, when we can't actually see these subatomic particles? We view the trail of the condensation that follows them. You were able to tell me a whole lot about these airplanes simply by viewing the condensation trail that followed them. We're able to determine a whole lot about these particles that make up protons and neutrons simply by observing the cloud path or the condensation path that follows them. Does that make sense? I'm sorry? Yep, no, that's right. That's right. No, you're absolutely right. You're absolutely right. That's a good point, Braden. Braden's saying, look, we've seen airplanes fly by, right? We see the condensation trail that follows them. We haven't seen these little charged particles go by, right? We can see the condensation trail that follows them after these tiny little charged particles ionize the molecules of this supersaturated air. But we can't see the particles themselves. Let's go back to the diagram again for a second, though, Braden. In this diagram, can you see the airplanes? No. In this diagram, you told me that there were two airplanes flying perpendicular to each other, blah, 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 without me ever mentioning the word airplane. Now, airplanes are within your realm of experience, right? So you see this and you say, oh, that looks an awful lot like what I saw in the sky yesterday. So the analogy doesn't quite work perfectly because you've seen something like this before. As opposed to if you're looking at this, you're going to see the cloud path and you're going to say, well, something's causing it. Even if you had told me, though, when you saw that diagram, right, and even if you hadn't known it was airplanes, even if you just said, all right, something's traveling this way, something's moving this way. We know that whatever it is that's moving this way has two engines that are causing condensation, and they're not hitting each other, and this one went by a long time ago, and this one went by not that long ago. Even if you didn't know they were airplanes, you know a lot about those things that produce those cloud paths, right? So even if we don't know what the particles are that are inside the proton, that make up the proton, we can at least learn a lot about them by following the cloud path. Another way to observe them is something we call a bubble chamber. This is real similar, but exactly the opposite at the same time. Here, instead of having a dust-free air supersaturated with water or alcohol, in other words, instead of having a gas that's really close to being a liquid, we have a liquefied gas. It's at low pressure, which lowers the boiling point. A liquefied gas, in other words, we have a liquid that's almost a gas. So cloud chamber, we have a gas that's almost a liquid. In the bubble chamber, we have a liquid that's almost a gas. Now, because we've liquefied this gas at a low pressure, we've lowered the boiling point to just above the temperature where we are. So if the temperature of this liquefied gas is 20 degrees Celsius, then the boiling point would be 20 point something degrees Celsius. So we're almost at the point of boiling this liquid. Almost, but not quite. When these charged particles, or these subatomic particles, these particles that make up the proton, go into this bubble chamber, then they ionize molecules again, just like it did in the cloud chamber. But this time, instead of the ionized molecules causing the vapor, the gas, to condense into a liquid, this time they cause the liquid to turn into a vapor. They cause the liquid to boil. So what are we going to follow this time? We're not going to follow a condensation path or a cloud path. We're going to follow a bubble path. When you boil water, you always see those bubbles rising to the top, right? Where this liquefied gas boils, you're going to see bubbles. And it's going to boil as these charged particles go through it. So let's follow the bubble path, and let's learn something about these charged particles that are causing this bubble path. So it's different in the sense that instead of having the gas turning into a liquid, we've got the liquid turning into a gas, but it's similar in the sense that the end result is pretty much the same. We observe the path of either the clouds or we observe the trail of either the cloud or the bubbles and get some information about whatever it was that caused that trail. Now this is a diagram of a cloud chamber. You can see that you got particles going everywhere. Some of them in a straight line, some of them in spiraling, some of them in circles. You got particles going everywhere. What do you think might cause these particles to go in circles? Yeah. Maybe a magnetic field. Okay, let's introduce a magnetic field into this. Let's introduce an electric field into this. If we introduce a magnetic field and we find that the charged particle curves a certain way, what does that tell us about the particle? Tell us that it's charged, yes. Okay, if it keeps going in a straight line in the magnetic field, then it's not charged. Okay? What do we know about, what do we learn about the particle based on the way that it curves in that magnetic field? The amount of charge that it has, right? Or the type of charge, I should say, that it has. The type of charge, whether it's positive or negatively charged. We can learn something about the speed by combining electric and magnetic fields. And I mean, we don't need to get into detail about everything that we can learn about this and how we're going to learn it. The bottom line is we can learn a lot just by looking at the natural cloud path that follows it, or the natural bubble path that follows it. But if we start introducing other things like electric fields and magnetic fields, we can learn a whole lot more. Does that make some sense? Now, what kind of particles do we actually get out of this? Well, this is kind of a big-looking chart. You have all this information in your notes already, the notes that I photocopied for you. But this is a tidy little chart, I think, that can come in pretty handy for us here. I'm going to write down a whole bunch of things. You need to know what I write down in red. Okay, what I write down in black or blue or green, it's for perspective. If I give you just the information that you need to know in Physics 30, you might be able to remember it, but it's not really going to make any sense to you because you're not going to have any context. So I'm going to show you a little bit more. You just don't need to remember all of this stuff. I just want you to see it again for context. We really have two types of particles. And those two types of particles really go up here. The two types of particles are, let's cover this one up here. Let's get rid of that, actually. We've got the bosons over here. That's a good name, eh? Boson. We've got the bosons over here, and we've got the fermions over here. The fermions are what I'm going to be concerned with the most here. Bosons are particles like photons, gravitons, particles that cause gravity, particles that are light. You've probably heard in the last 6 months of a rather famous boson. Right now, this isn't part of our curriculum. Right now, we don't have to know this. Probably the next curriculum change that will happen in a few years, we probably will have to know about bosons because it's been all over the news over the last 6 months. You guys ever heard of the Higgs boson? The particle that's been theorized for 50 years, but was discovered about 6 months ago in the Large Hadron Collider in Switzerland and France. It's the particle that we believe is responsible for mass, the particle that we think causes mass. There's a bunch of different types of bosons. We're not going to concern ourselves with that so much because we don't need to. The fermions, however, we are going to concern ourselves with. We need to know about fermions. There are two subcategories of fermions. They are the leptons. Notice I'm doing this in red. The leptons and the hadrons. The leptons are particles that are not mediated by the strong nuclear force. In other words, not affected by whatsoever the strong nuclear force. The strong nuclear force has no effect or bearing whatsoever on these leptons. These leptons, as far as we know right now, are fundamental particles. You can't get any smaller than these leptons. An example of a lepton would be an electron. We said a few minutes ago that protons and neutrons can get smaller. I never said anything about electrons. Electrons, as far as we know, are as small as it gets. Another example of a lepton would be an electron neutrino. An electron neutrino is the type of neutrino that we've talked about when we were talking about beta decay. When you get beta negative decay, or beta positive decay, I should say, a neutron changes into a proton, beta negative decay. A neutron changes into a proton and an electron, you get an antineutrino produced. When you get beta positive decay, a proton changes into a neutron and a positron, you get a neutrino produced. The neutrino that we talked about with beta negative and beta positive decay is an electron neutrino. Now, there are other types of neutrinos as well. But because the only type of neutrino that we ever deal with in Physics 30 is an electron neutrino, we often just drop the electron word in front of it and just call it a neutrino. Now, the other types of leptons that we don't need to know about are the tau neutrino, the muon, and then we've got the muon neutrino. Plus the antiparticles of all those. What's the antiparticle of an electron? Positron, an anti-electron or positron. What's the antiparticle of a neutrino? The antineutrino, or the electron antineutrino. You could have the anti-tau, the anti-tau neutrino, the anti-muon, the anti-muon neutrino, although you don't need to know about those. These are our fundamental particles. We don't get any smaller than these. Hadrons are not fundamental particles. They get smaller. They are mediated by the strong nuclear force. A couple examples of hadrons. A proton is a hadron. A neutron is a hadron. In the Large Hadron Collider, we smash together protons. Why do we call it the Large Hadron Collider? Because we smash together hadrons. We collide hadrons. We collide protons. These hadrons, these protons and neutrons, are made up of or consist of quarks. Leptons are basic building blocks of matter, as are quarks, basic building blocks of matter. The electrons go into the atom themselves. The quarks combine together to form hadrons, which go into the atom themselves. There are 6 types of quarks, 2 of which we need to know about. We need to know about the up quark and the down quark. But there is also the top quark and the bottom quark. There is also side quark and the front quark. It's even worse, actually. There's also the charm quark and the, do you know this one? Ugly, did you say? I thought you said the ugly. The strange quark. The up quark, the down quark, the top quark, the bottom quark, the charm quark, and the strange quark. We need to know about the up quark and the down quark because those are the quarks that combine together to form protons and neutrons. By the way, we also have the antiparticles. We have the anti-up quark and the anti-down quark. The anti-top, the anti-bottom. You would think the anti-top would be the bottom, but it isn't. Anti-top, anti-bottom, anti-charm, anti-strange. Yeah, you'd think the anti-up would be the down as well, but it isn't. Each of these has a charge. The charge of the up quark is plus 2/3 of the elementary charge. The charge of the down quark is negative 1/3 of the elementary charge. The charge of the top quark is plus 2/3 of the elementary charge. The bottom quark is negative 1/3 of the elementary charge. What do you think the charge of the charm quark would be? 2/3 of the elementary charge. And the strange quark would be negative 1/3 of the elementary charge. What would the charge of the anti-up quark be? Negative 2/3. What would the charge of the anti-down quark be? Positive 1/3. See what the difference is between, say, a down quark and an anti-up quark? A down quark has a charge of negative 1/3. An anti-up quark has a charge of negative 2/3. These are matter. Up quarks and down quarks are matter. An anti-up quark and an anti-down quark are antimatter. When they come together with matter, they annihilate each other and produce a lot of energy. I'm sorry? I don't know. I'm not sure where that came from, actually. No, you know what? I read that once. It came from a book, like a novel. I can't remember which it was, though. Whatever novel it was, somebody just at some point said, I like that word, basically. I'm going to steal that word and I'm going to apply it to this. Just like a fiction, literature. Just liked it and applied it. I can't remember what the book was, though. It's a pretty famous book, but I can't remember what it was. Yeah, go ahead. Well, that's a good question. The leptons and hadrons that we've talked about, yes. But there are other leptons and other hadrons as well. So, you know, we've got the tau neutrino, the muon neutrino. What we have to understand here is that we're going beyond, at this point, an atom that we typically think of as being an atom, and we're talking about other forms of matter now. So the electron is a particle that exists outside the nucleus, yes. And the hadron is a particle that exists inside the nucleus. And I guess in that sense you can say, well, yeah, of course, that makes some sense, because the electrons are not mediated by the strong nuclear force, and the hadrons are mediated by the strong nuclear force. So yeah, I guess in that sense it makes sense that, you know, these guys would be inside the nucleus, these guys would be outside the nucleus. But don't misunderstand this. In a typical atom, we don't have a bunch of taus and muons orbiting around the atom. Okay, does that make sense? So if they're in an atom, then yes, they wouldn't be part of the nucleus. But the electron is the only electron that's part of the typical atom. Well, we've actually, I say we, scientists have actually created atoms with other particles other than electrons in them. But they only exist for a very, very short period of time. Right? They don't exist naturally, at least here on Earth. They don't exist naturally, and nor do they exist for any more than a tiny fraction of a second. So it's basically an exercise in, can we do it? Yes, we can do it. Beyond that, that's kind of where it ends, at least right now. Let's take a look at beta decay again, that we looked at earlier on in this unit. Two types of beta decay that we see here. Tell me what this U means here. No? It's a good guess, atomic mass unit, you'd think, right? This means an up quark. The D means a down quark. So let's take a look at the charges here. The charge of an up quark is what? Positive 2/3. The charge of a down quark is negative 1/3, and the charge of a down quark is negative 1/3. When we add those up, what do we get for a total charge? What kind of particle do we have there? That's a neutron. So an up, down, down is a neutron. We have three quarks combining together to form a neutron. Let's see what we have over on the right-hand side. Up, up, down. That's 2/3, 2/3, and negative 1/3. What's 2/3 plus 2/3 plus negative 1/3? 3/3, or 1. 1 times the elementary charge. What do we got right there? It's a proton, right? And what's this thing right here? Well, that's an electron. That's not made up of quarks, is it? Because the electron is a lepton. It's as fundamental as it gets. So it is what it is. What's this thing right here? The anti-neutrino. So what kind of decay do we have here? Beta what? Beta negative decay. We've got a neutron changing into a proton and an electron, and we have an anti-neutrino produced as well. Let's take a look at the next one. Up, up, down. Up, up, down is, well, we said that it was a neutron, sorry, a proton a minute ago, charge of 1 elementary charge. Let's just double check that. Up is 2/3, up is 2/3, down is -1/3. Let's add those up and we end up getting 3/3 or 1 elementary charge. Yeah, we were right, it is a proton. Take a look at the next one, up, down, down. We said that it was a neutron, but let's double check that one as well. We have 2/3, -1/3, -1/3. We add those up and it gives me 0. That's a neutron. Right now, let's just pretend that doesn't exist there. We'll go back to that in a second, but let's, for now, pretend it's not there. So we have a proton that is changing into a neutron, and what's this thing right here? That's a positron, the antiparticle of an electron. And what do you got right here? That's a neutrino. What kind of decay is this? When a proton changes into a neutron and a positron and a neutrino. What is it? Beta positive. Now, what is this whole thing that I scratched out in here and said, let's not pay attention to right now? You don't really need to know that, but I'm going to tell you anyways. Beta positive decay is really a two-step decay. It doesn't happen all at once like beta negative. Beta negative, you get the up, down, down, the up, up, down, goes to the electron and the antineutrino. The neutron changes to the proton and the electron, and the antineutrino is done. It's all one step. It's all, you know, once part of it's done, it's done. But beta positive decay occurs a little bit differently. Beta positive decay occurs this way. We get a proton, it changes into a neutron, and then this little thing that we call a virtual particle. And then the virtual particle decays into a positron and a neutrino. So it's kind of a two-step process. But as far as you're concerned, it's fine to assume it's a one-step process. It doesn't really matter to us that it really takes place in 2 steps. We just need to remember what we learned back in the unit when we learned about beta positive decay. You get too many protons, so what happens? A proton changes into a neutron and a positron and a neutrino, and the positron and the neutrino get kicked out of the nucleus. Okay, the fact that it happens in 2 steps doesn't really matter to us at all. That make sense?